Berlin, the German capital, is a 21st century metropolis in the heart of Europe. It has a long history, famous historic buildings and unique architectural monuments from various eras through to contemporary architecture. All these modern buildings and projects consist of quality-controlled construction materials with selected characteristics, extreme resistance and high demands on environmental compatibility, on static equilibrium and structural safety. The company testing Bluhm and Feuerherdt is based in this European city. In its modern production facilities, Testing, one of the most renowned German providers of complete construction material testing laboratories, manufactures testing machines, premium laboratory devices, as well as stainless steel laboratory equipment of the highest quality. Our product portfolio contains around 3,500 different, mainly standardized products. For new and further developments, we have experienced mechanical engineers, electricians, hydraulic specialists and concrete experts at our disposal. Here, a new Blaine device is being developed in the engineering department. We currently produce the widest range of Blaine devices worldwide, from simple hand-operated devices to computer-controlled automatic models. The electronic Blaine device Dukerhoff system number 1.0210 is used exclusively to determine the grinding fineness of pulverized materials such as cement. It should only be used for its intended purpose. To determine the grinding fineness of cement, its specific surface area must be established from the air permeability of an accurately defined compacted cement bed. This is done by observing the time taken for a fixed quantity of air to flow through the cement bed. This time is then a measure for the specific surface area, which is indicated in square centimetres per gram. The laboratory, testing equipment and test material must have a temperature of between 18 and 22 degrees Celsius, as well as a maximum relative humidity of 65%. Inspect the visible condition of a delivered consignment immediately. Any damage which occurred during transport or a shortfall in quantity must be logged without delay and submitted to us by fax or email. Use the delivery note to verify that the consignment is complete. It must include the electronic Blaine device, Dukerhoff system with network cable, permeability measuring cell with plunger and perforated disc, tamper, syringe with tube for filling and manometer liquid, packet of 41mm paper filters, foam plug packaging unit, filling funnel, operating instructions and an application DVD. Not included in the delivery scope but necessary tools and aids include reference substances of differing grades of fineness, precision balance accurate to 0.01 grams, a fine brush, a bottle with a screw lid, a digital vernier caliper accurate to 1/100th of a millimetre or a depth gauge accurate to 1/10th of a millimetre, a spatula and bottle brush, a measuring spoon, and a dial gauge for determining the remaining distance. Irrespective of the type, the Blaine device must first be set up and aligned on a stable, level and vibration-free surface. With the aid of the filling syringe and tube, the manometer liquid supplied is sucked in from the bottle. Approximately 60 millilitres is required. During the filling process, the end of the tube is inserted into the left side of the metal casing in the U-tube. Ensure that the tube can be seen in the U-tube so that the manometer liquid also reaches the tube. The manometer liquid is carefully filled into the U-tube. The U-tube must be clean and dry before being filled. The filling level gauge is reached. The most important components of the electronic Blaine device are the start button, the time counter, the measuring section with the two photoelectric barriers, the U-tube manometer, the permeability measuring cell, and the connection support. The measurement takes place on the section between the two light barriers. Position of the filling height. The opening for filling the manometer liquid into the tube. The power plug and main switch. Determining the apparatus constant K. As the Blaine method is a comparative test between a known and an unknown material, a reference sample with a known specific surface area as a comparison is required in order to determine the apparatus constant K. As supplied by the manufacturer, the device is, as a rule, not calibrated. Calibration must be carried out in which the apparatus constant K is determined for the reference substances. This is required later in order to calculate the Blaine value. If the apparatus constants have already been determined, testing can begin immediately. The power plug is installed and the switch turned on. In the measuring cell, the perforated disc is inserted and pressed with the tamper up to the stop. Then 2 paper filters are inserted and also slid into a flat position on the screen floor. All cell dimensions are accurately determined to 1/10 of a millimetre. The depth gauge is used to measure the internal height of the measuring cell at 6 different points and the mean value calculated. Then the diameter of the cell, G, is measured at 6 different points and the mean value is calculated. Finally, the plunger length, F, is determined at 6 different points and a mean value is calculated. Now, the powder bed volume can be mathematically calculated from equation 1, which includes the inner dimensions J of the cell, the plunger length, F, and the cell diameter, G. With the powder bed volume V and the known and adopted data of the reference substance, the mass M0 of the bed is exactly weighed out using equation 2 to 0.01 grams. In this, E represents the porosity of the reference substance, ρ equals the density of the reference substance, and V the powder bed volume. The apparatus calibration is now carried out on the basis of these selected test substances. The corresponding apparatus constant is now determined for this reference substance. The selected test substance is shaken for at least 2 minutes in a bottle with a screw lid to dissolve any agglomerates. The bottle is then left to stand for 2 minutes. Subsequently, the powder bed is stirred with a clean, dry rod in order to evenly distribute the fine particles. Insert the perforated disc into the clean measuring cell and ensure that it lies flat on the lower edge. Place a filter paper disc on the bottom of the measuring cell, making sure it is lying flat on the bottom. Accurately weigh the calculated sample weight of the reference substance to 0.01 grams on a precision balance. Different tools can be used in the laboratory. The surface of the powder bed can be levelled by lightly tapping on the cell wall. A second filter plate is laid on the surface of the reference material with the aid of the tamper. Now the reference material is compacted by slowly pressing the plunger so that, without exerting any great pressure, the lower face of the cup is in contact with the upper edge of the measuring cell. The plunger is slowly raised slightly, rotated through 90 degrees and pressed on the material again. Finally, slowly withdraw the plunger without disturbing the powder bed. The suction tube to which the measuring cell is attached must be fitted with a dust filter. The measuring cell is placed on the connection support and fitted on the bayonet lock. Briefly press the start button to test it. The manometer liquid is sucked in. Once the required level has been reached, the pump stops. The oil level drops slowly. On reaching the upper light barrier, the time measurement begins. This runs automatically. The time measurement stops when it passes the lower light barrier. Three measurements are carried out for the reference substance. The temperature must also be recorded. A second and third test are prepared with new material and carried out again for each three measurements and the mean value calculated for each test. The same applies to the temperature in degrees Celsius. The apparatus constant K is determined by each reference test to 2 places behind the decimal point from equation 3. In this, there is S0 equals the specific surface area, ρ0 equals density, T0 equals flow time, eta equals air viscosity, and E equals porosity. A sample calculation. The apparatus constant of test 1 is determined from the mean value from 3 runs. A mean value is again calculated from the 3 apparatus constants from the 3 tests, which is then assigned to the tested comparator substance. In principle, the appropriate apparatus constants are determined for different grades of fineness. Calibration or recalibration is carried out for first use, after 1,000 tests, for a different type of filter paper, for another type of manometer liquid, for new perforated discs, for a new manometer tube, and in case of systematic deviations of the secondary reference cement. If the measuring section on the device is changed, the apparatus constant must also be re-reckoned. The apparatus constant is not transferable to other devices, not even to the same models. Determining the specific surface area of cement. Procedure. Using the example of cement, a grinding fineness test is carried out by Blaine. First, a perforated disc is inserted in the measuring cell and pressed onto the lower edge with the tamper. Then, a paper filter disc is inserted and pressed onto the perforated disc. A sufficient quantity of the cement to be tested is filled into a jar with a screw lid and shaken vigorously for 2 minutes to dissolve any agglomerates. Then leave the sample to stand for 2 minutes. Subsequently, distribute the fine particles with a dry, clean rod. The calculation of the cement sample weight takes place according to equation 5, whereby the volume of the cement bed must be known. If this is not known, it must be determined as described in the chapter Determination of Apparatus Constants and calculated. The density of the cement is known or must be determined. The porosity is initially accepted as 0.5. The mass of the previously calculated cement bed is now weighed and poured into the measuring cell. Level the surface of the cement by gently tapping the measuring cell. Then place another filter paper disc and press it down with the tamper. Compact the bed slowly and continuously with the plunger until, by exerting slight pressure, the lower face of the cup is in contact with the upper edge of the measuring cell. Carefully raise the plunger, rotate it through 90 degrees and compact again. Carefully withdraw the plunger without disturbing the cement. Place the measuring cell on the nozzle and turn the bayonet lock. Briefly press the start button. The pump extracts oil until it reaches the upper suction point. As soon as the fluid meniscus reaches the upper photocell of the measuring section, the starting point, the measuring process begins and the dial gauge starts to run. When the liquid passes the lower photocell of the measuring section, the measuring process stops. The lead time is indicated on the counter. Time and temperature are noted. The measuring process is repeated and the results are again noted. The sample is pressed out of the measuring cell and a second sample is prepared as before from new cement and also tested twice. Note the results of the lead time and temperature. The specific surface area S of the cement can now be calculated. The apparatus constant is hereby K, which has a similar Blaine value as the tested cement. E is the porosity of the cement bed. Rho is the density of the cement. Eta is the mean value of the two test temperatures and T the mean value of the two lead times. A sample calculation. The apparatus constant amounts to 17.99, the porosity 0.5. The time as a mean value amounts to 55 seconds. The density of the cement is 2.65 grams per cubic centimetre. The viscosity of the air is accurately determined to within 1 degree as a mean value at 22 degrees Celsius. The specific surface area S1 of the cement can now be calculated from the mean value of the two measurements. Two samples must always be tested in order to establish the total mean value S of the specific surface area. A mean value is now calculated from the specific surface area S of the samples 1 and 2. The value is rounded to the next 10 square centimetres per gram. Optionally, a dial gauge can be used to determine the possible remaining distance in a compacted cement bed. The dial gauge should initially be installed on the cell. The display value must be positive. To adjust the value, use the button on the display. The timer is set to 0. In this example, the remaining distance of the sample is 4.82 millimeters due to too much sample weight as a result of incorrectly assumed porosity. However, a new cement bed does not need to be prepared. The additional volume V bar is calculated and the old volume is imputed so that V double bar is the result. The actual porosity can be determined with equation E. The determination of the two lead times follows as usual. With the newly determined porosity, the mean value from the two flow times and the temperatures of the sample, the Blaine value can be calculated. All other regulations apply as usual. If a sample weight is too low and the plunger falls through, the cement bed must be recalculated and reproduced. Alkalis are released when mixing cement and water. Immediately remove any wet or dry cement which comes into contact with the skin. If cement gets into your eyes, wash them thoroughly with clean water and seek medical attention immediately. Protective clothing, rubber gloves and glasses should be worn. Should the measuring section be altered between the starting and stopping point, all apparatus constants must be redetermined. The amount up to the filling mark can then vary, since it's dependent on the measuring section of the adjusted lower light barrier. If the electronic Blaine device has to be shipped, repaired or disposed of, the manometer liquid must be removed, otherwise there is a risk that the electronics could be destroyed. The liquid should be sucked out with the suction syringe. Never attempt to pour out the liquid. The device may be returned to the manufacturer for repairs or factory calibration. This video clip shows the use of the Blaine device produced by the testing company in Berlin for the visual clarification of the test and calibration process. The video does not replace current test standards, the guidelines of authorized personnel, or the official operating instructions of the Blaine device. National safety regulations must also be observed. The shown sample calculations are fictitious and should not be adopted. All values must be determined for the first time by the user and on an individual basis.